So our first speaker this afternoon is Kirone Mallick from Institut de Physique Théorique, IPHT, from Saclay in France. And he will talk about dynamical fluctuations in Riesz and Dyson gases. So please, Kirone, the floor is yours.
Thank you, Gregory. Thank you to all of you. It's a great pleasure. I'm grateful to the organizers. It's a pleasure to be here and to see again many people who are dear to me. I'm going to tell you about dynamical fluctuations in Riesz and Dyson gases. It's a subject I started working on only recently. Many people here are experts, including the ICTS group in particular, so I'm not completely at ease. Anyway, I will try to explain to you that some coarse-grained hydrodynamic viewpoint on these long-range interaction gases can give you some interesting results. So I'll deal with the Riesz gas, I'll define it later, the Dyson gas, and the third part, which I will have no time to talk about, apart from the conclusion, will be about free expansion of a gas with long-range interactions. So these are common works done with Raoul Dandekar, who was a postdoc during 2 years in Saclay, who was really at the core of the progress in this work, Paul Kravkiewski and myself. So one paper is published, the other one is accepted, and the third one should appear in arXiv tomorrow, in a few days. So just to begin with, and some basic considerations, usually it's only the basic things that people remember, and I think the message is important. There is one phenomenon which is known as single file diffusion, which is the transport of macromolecules in a thin capillary vessel. So if you have a tube which is quite wide and the small particles which are performing Brownian motion inside it, if you tag a particle, it will diffuse normally. X square is proportional to time. But if you have a very thin capillary vessel and big macromolecules that cannot overtake each other, then the order is preserved. And in fact, you have anomalous diffusion. X square is like square root of t. So the scaling is t to the power 1/4. So that's single file diffusion, anomalous diffusion. And it is very well understood now for many years, many calculations, and even experimental realizations have been made almost 20 years ago in Stuttgart in Beschinger's group. If you have single file diffusion, you have anomalous diffusion. If you make a bigger tube, then you have normal diffusion. So for this model, again, symmetric exclusion is a pristine model. So symmetric exclusion is a set of random walkers on one-dimensional line. So the red balls are random walkers. They perform continuous time random walks with one very important ingredient is that two balls cannot sit at the same site at the same moment. You have this exclusion, classical exclusion condition. So now suppose we observe a given particle, we tag one particle here, and we call its position xt with time. It started at 0. If there was no constraint at all, of course it was diffused normally, but here, because of this order-preserving constraint, the position of the particle will display some unusual features, anomalous diffusion, and also the current of particles through a given link will be closely related to the position of any particle because they cannot overtake each other. So, if you just want to take a message with you from the beginning, it's that, of course, on the average, because of symmetry, the average position of a tagged particle is 0. But if we now look at the variance, x square average, if it were not interacting, it would be normal, but because it's interacting and there's this exclusion condition, x square scales like square root of t, and even the prefactors are exactly known in the large time limit. So this is an exact result more than 40 years ago by a mathematician called Aratia. But the full distribution of the tag particle distribution remained unknown for many years. There were quite a few mathematical papers, large deviations and so on, but the exact diffusion was not known. And only recently, an exact formula valid for any time has been obtained for x of t, for the exclusion process, for the microscopic model. And in parallel, just a year later, coarse-grained description using fluctuating hydrodynamics and using this macroscopic fluctuation theory that I'm going to tell you about, allowed to retrieve these results macroscopically. So this is a very nice, if you want, academic example, mathematical example, in which we have a full understanding at the microscopic level. using combinatorics, integrable probabilities, better ansatz. And we have also a complete understanding at the macroscopic level using hydrodynamics and classical integrability, inverse scattering, and so on. And these two approaches perfectly match. So I'm going to just go through the results in 1 second. This is not the object of my talk, but just to tell you what it looks like. At the microscopic level, there is a formula for the characteristic function of the position of the tracer in terms of a Freedom determinant. So it's an exact formula for any time, and this Freedom determinant can be analyzed asymptotically and can be used to compute the variance, for example, and retrieve Aratia's result, but also higher orders and asymptotics and so on. At the macroscopic level, so the description of this gas, this fluid of interacting particles, it's a kind of liquid, but it obeys some unusual equations. So if you look at the fluctuating hydrodynamics or the macroscopic fluctuation theory for this model, you have to introduce 2 fields. One field is the density field, which we usually call Q, and there's another field which is a conjugate momentum or response field, which we call P, and the equations satisfied by the fluid, so momentum and position, are coupled PDEs, deterministic coupled PDEs, and somehow the large-scale behavior of your fluid is entirely embedded within these equations. So these equations have an Hamiltonian structure, and they have been written already almost 20 years ago by the group of Rome around Gianni Gionalazino, and these equations contain the macroscopic non-equilibrium fluctuations of the symmetric exclusion process, or in fact of any diffusive system. The only thing you have to know in these equations is the diffusion constant here and the conductivity sigma, and once you know them from some microscopic calculation, then you have macroscopic equations that you can try to solve and study. Okay. So using classical integrability, which means, if you want, soliton theory, inverse scattering, you can solve these equations and obtain the characteristic function of the current, which is closely related to the characteristic function of a tracer position at macroscopic level. So this is a very simple formula, almost 3/2 polylog function. And this macroscopic result matches perfectly with the asymptotics of the microscopic Freedom determinant that we have. So this introduction is just to tell you that for at least one or a few very special models, like the symmetric exclusion process or the KMP model, there is a large body of knowledge and large body of technologies that allow you to understand what's going on. So now we want to extend this approach, and we want to understand other kinds of systems. So many questions arise. For example, if your model, which is underlying your dynamics, is not integrable, what can you do? So you can do perturbation theory. And using perturbation theory with Paul Krapivsky and Tridib, 10 years ago, we were able to compute the variance of your tracer for any sigma and d, so not necessarily the exclusion process. And there are some nice features in this formula, some memories of the initial conditions, and so on. Higher cumulants have been computed, 4th cumulant, very recently by Benichou and Grapsch, again doing perturbation theory, and it's still open to know whether the full series, the full generating function, can be understood. So the main question I want to address today is, do these results that we have for this very simple stochastic interacting particle system, do they generalize to some non-diffusive single-file systems, for example, gases with long-range interactions? And in fact, the very reason for this seminar, and I'm very happy that Herbert is here, is a question that Herbert asked me almost 9 years ago in Nice. He told me about a result he had for the Dyson gas, in which the variance of a tracer in a Dyson gas grows asymptotically, it should be asymptotically equal, as a logarithm. And he told me, can you ask me whether this kind of result could be retrieved using a hydrodynamic approach? So I'm going to answer this question at last that Herbert asked. So can we retrieve this logarithmic growth of the variance of the tracer, very slow growth, and can we get higher cumulants in the Dyson gas and possibly some other classes of gas which are known as the Riesz gases. Another question that one may ask is that once you have tagged a particle and you look at its trajectory, you can ask what are the statistical properties of this object. In the case of the symmetric exclusion process, Pelligrad and Seturaman proved that a tagged particle trajectory asymptotically goes to the fractional Brownian motion 1/4. So you may ask this question for more general gases. So let's start with the Riesz gas. So what is the Riesz gas? A Riesz gas is a simple mechanical system, an overdamped system of n particles, denoted their position in one dimension, denoted by xi, that interact by this inverse power law potential. Okay? So in particular, you have the Coulomb gas, which enters this thing, and they are subject to some thermal noise, so independent white noises. So it's a very simple system of interacting particles, but the main difference is that now it's in continuous space as compared to the symmetric exclusion, and possibly, if S is not too large, the interaction is short-ranged, is long-range, sorry. So the Dyson gas will come as a special case for S equal to 0, okay? It will be the second part. So this is very general. So Riesz gas and Dyson gas is a special case. So for S bigger than 1, the gas is short-ranged, and we don't expect anything different from very local interaction like in the ZEP. For S between 0 and 1, I don't consider negative S, although it's possible. The gas is long-ranged, and the free energy is non-local. So our goal is to generalize this MFT approach and investigate fluctuations of the current and the position of a particle in an initial setup with a uniform density. So I'm going to give you some very basic features and then give you the results without explaining how we got them. First of all, there are 3 parameters in the system: the interaction strength, G, the amplitude of the noise, D, and the initial density, rho, of the system. And you can build only one dimensionless constant in your model. So we will set G and D equal to 1, okay, small J, sorry, J or G? G? G, okay, G and D equal to 1, and keep this capital G as a parameter. And we shall focus only on the long-range case. And of course, very naturally, the number of particles being conserved, we have the continuity equation. And this equation is a priori not closed because we don't know how to express the current as a function of the density, but working a bit more, we can find a closure for this equation and express the total current as the sum of 3 contributions, a gradient term, which is natural, a term coming from the noise with the amplitude square root of Q, which denotes the fact we have Brownian motions underlying the dynamics, and the Riesz noise, which is due to the interactions. So all this can be done cleanly. And the only thing we need is to know the expression of the Riesz noise. And the expression of the Riesz noise is the density Q times this integral, which in fact is just the potential created at a given point by the other particles, the force precisely. And this kernel, again, if you take S equal to 0, this is the so-called Hilbert transform, but it's a kind of generalized Hilbert transform. So now we have every ingredient, we have a closed equation in terms of this density Q, and we can even write a free energy for the system. So this will give you the interaction current, and this will give you the diffusive current. So all this is very well explained in papers of Abhishek, Anupam, Gregory, Satya, and their students. Okay, so all in all, if I rewrite my continuity equation, I get a nonlinear stochastic PDE, and this is exactly in the spirit of Dean and Kawasaki equation. Okay? So once we have this kind of Dean-Kawasaki equation, the usual procedure to compute things is to write a path integral. Because we have a noise, we can write a path integral. I'm interested in the statistics of the total current, which has flown through the system, through, let's say, the origin of the system between time 0 and capital T. So I can write the characteristic function of this total current as a path integral. And this path integral, so doing the usual Martin-Sigia-Rose, call it as you prefer, transformation, I can write an effective action for this model, which is given here. So again, I'm rushing, but the main idea is you have this Dean-Kawasaki equation, you write a path integral, you are in the long time limit, you're interested in a saddle point, you write the Euler-Lagrange equations for the saddle point, and you get these equations. So these are, yes, Abhishek?
You don't have a trap.
There's no trap?
There's no potential.
So yes, there is a very, very, very shallow trap, which I put vanishingly small in the limit. The initial condition is in the center of the trap, so it's flat, a flat initial condition. So these are the equations that I'm interested in for this Riesz gas, and the initial conditions, which in fact are obtained also by variational calculus. If you look precisely at this Q and do the variational calculus, are given by these blue equations. So at least at this stage, the mathematical problem is well defined. I have this set of, these are not exactly PDEs because H is an integral operators. So integral differential equations coupled with these initial conditions. And if I'm able to solve that, I know the statistics of my current in my Riesz gas. So unfortunately, we have been not able to solve it, but we could solve it perturbatively. And once we solved it perturbatively, we could compute the variance of the current. So this is an exact expression. We could compute the variance of the position of a particle. That's very closely related to the current because there's no overtaking possibility in these equations, in these systems. And we could also compute the correlations between the position of two particles. And this correlation is, of course, remindful of a fractional Brownian motion with exponent s over 2s plus 1. So you see that there's an anomalous diffusion here, naturally, okay, because time is to the power s over s plus 1. And if we look at things in more details, we see that in short-range forces, we do have this anomalous diffusion exponent s over 2s plus 1. And as soon as the forces are long-ranged, s bigger than 1, then we have the universal t to the power 1/4 single-file behavior. So we match this universal behavior, but for low values of s, we have a constantly varying exponent of anomalous diffusion. So now some limiting cases. So for s equal to 1, it's a kind of special case mathematically. You can even look at the formulas, they become singular. The operator here becomes singular, it's x squared if you want, 1 over x over x cubed. And even the perturbative calculation fails, but anyway, you can, doing some kind of, hand-waving argument, you can guess that x squared is of the order t over log t. So one frustrating thing is that we cannot solve these equations completely, only perturbatively, and even higher cumulants seem to be complicated to get. For example, the fourth cumulant would involve some complicated calculations, and so we didn't get it yet at the moment. Another piece of information which is quite important, especially that the chairman is sitting here, is that more recently, a few months ago, Tuzo, one of your students, Pierre Ledoussal and Grégory Cher, used a different approach. They linearized the dynamics of the system near crystalline order. So they linearized these equations near the crystal order, and they obtained many more, but they also retrieved the formulas that I have written here. So they got the same. And somehow I think it's comforting for me because going to hydrodynamic limit without proving it and so on is a bit shaky, but the fact that your calculation got it back proves that this is correct. Okay, so when S is equal to 0, this is the Dyson gas. And now I'll turn to the Dyson gas for itself. So the Dyson gas are particles with an inverse 1 over x potential. So just given by x dot is equal to 1 over xi minus xj plus a noise, and they naturally appear in the random matrix theory. Okay? These are the dynamics of eigenvalues of dynamical random matrices. So this is a very, very important model, and it's also a very rigid system. The fluctuations are small, they are logarithmic. This is the old result of Herbert Spohn, and also many results also in random matrix theory on number counting of eigenvalues on some intervals. It's known that fluctuations are relatively small. So our goal is to understand this kind of results, and if possible to get more, by using hydrodynamic approach, so these macroscopic fluctuations of interacting particle systems, and develop this hydrodynamic viewpoint. So I'm not going to write again, but you can do it by yourself now. You write the Dean Kawasaki. I think David should be here somewhere. He was here. Each time you hear the word Dean equation, you make a mark, yeah? Okay, so you can write this equation. You can write the path integral. You can do the saddle point procedure, Euler-Lagrange equations, and you get this nice set of equations. So this is a nice set of equations. This is the same as before, specialized for s equal to 1. One more feature, kind of educated feature from the previous result, previous calculations. There was a diffusive term in the previous equations, but in the long space and time limit, this diffusive term, the second derivative, is subdominant. So it will not interfere, and so I just killed it. And now we have the real Hilbert transform. There's a little difference, is that maybe I forgot a pi here. In the usual Hilbert transform, there's 1 over pi. So I put it back. There's a pi here, and I forgot a pi here, because I just copy and paste the equations. Yes. Anyway, so now we have to solve these equations and their boundary conditions that I'm not going to write again. But the nice feature of the Dyson gas, contrarily to the Riesz gas, is that these equations can be really analyzed non-perturbatively. We don't need to do perturbation calculation. There's so much knowledge and so much hidden integrability in this model. By the way, this model is not doing too bad with time. I'm finishing. So just one of the messages is that many techniques were developed for simple interacting particle processes, like the exclusion process, KMP model, these Markovian stochastic models, but they can be extended to long-range gases, and they can be used to compute fluctuations, dynamical fluctuations in these long-range gases. At least for the Dyson gas, it's possible to do analytic progress, and I even imagine that there should be a microscopic exact solution for this Dyson gas, maybe using the mapping to Calogero, just as there was a microscopic solution for ZEP. So there should be a complete picture. That's what I hope. At the moment, we don't have it. For the Riesz gas, it's a bit more subtle. If you try to do perturbation theory further, there are some subtle divergences. You have to put some cutoffs, and to be frank, for the moment being, I don't really know how to do that, but I believe it's just, if I don't do it, somebody else would do it. I mean, it's just incapacity from my side, but I think it's possible to do it. And the last thing I didn't tell you about, but the recent work we did with Paul Krabisky is just a deterministic calculation, which has very nice features. If you start with these repulsive gases, and you put n particles at the origin, at the initial time, and you let the thing flow, you obtain nice scaling behavior of the profile, and you can solve it at any times, even at finite time, and get the way, and see how it converges to equilibrium. It's not really equilibrium, it continues flowing, but you can see the dynamics of the system. Okay, I think I'm done.
Yeah, okay, thank you very much. Thank you very much, Kirone. So we have time for questions.
Just for the Riesz gas, you showed that the xt1, xt2 two-point correlation function is like a fraction bounding motion t1.
Yes.
But this is only two-point function. It's
Yes,
not
yes,
a fraction bounding motion.
No, of course. This hints behaves as. So in the case of ZEP, there's a nice proof of Setoraman and Pelligrad. They really proved it. I'm totally unable to prove it, but my hope is that maybe it's true. It's true. I mean, I would bet a reasonable amount on that.
Questions?
Yeah, one question. I was just confused by your very last remark about that the Dyson model is likely to be solvable I mean, it's a determinantal process. I mean, so isn't that already saying it's solvable? Or?
Yes, it's more or less what I meant, but I wanted. It's a determinantal process, but we still don't have a nice formula for this exponential lambda q, a bit like ZEP. But of course, as you say, well, of course, it's a determinantal process. So everything is there. 10 years more, Herbert, to answer this question. No.
You mean it depends on the initial conditions or no? No.
It's only for beta 1, 2, and 4 that's.
Okay. So it's only beta equal to 2. Yeah, okay, that's
true.
Go ahead.
Sorry, just one question. Maybe you mentioned it. But when S is less than 0,
Yes.
Does it go through or is there some problem? Because the model is still okay, right?
Yes, the model is still okay. I have a psychological problem with S negative. I don't know why. I just refuse to look at it. I will do it. Yes, it's the famous plasma. Of course, no, I know you studied it, but I just decided to look only at positive. Otherwise, you have to put this potential.
Yes.
You really have to put it.
Yeah.
And in some sense, I want to get rid of it.
Okay.
But I promise I will still sit and try to think about it. I don't know, my mind refuses to think to S negative.
Thanks.
How do you deal with the singularity when you study the problem where the particles are initially in a single point?
Can you say it again?
Sorry. How do you deal with the singularities when you're putting all the particles in 0?
Oh, because I'm at finite n. And because I'm at finite n, okay, it's not exactly 0, it's okay. So I'm not taking the continuous limit, so I don't have this operator. Okay. So it's true that I put my particles, so now I have a discrete problem with a finite number of particles, and I put them very close to each other, but not exactly at 0.
Okay. So let's thank Kirone again.
Long live India and France friendship.